So today we will learn how to use linear regression in order to solve a classification problem. It is a different learning paradigm compared to the one that we saw last week, the concept learning paradigm. And since this will not take very long, we will also look a little bit in the beginning of the evaluating effectiveness slides. The starting point is something that you already saw in the beginning, namely the prediction of whether customers of a bank are creditworthy or not. But we could also solve a different kind of problem here, given a set of customers, a set of n customers who are represented in a p-dimensional vector space, namely a regression setting, a regression problem. We could try to predict their credit line, so how much of a credit they are worth, given the data we know about them. And we want to do that with a so-called regression function that has a range of the real values. And for each customer that we have in our database, we know a ground truth value for the credit line, which is yi. For the ith customer, we know we know their credit line. And we are given n examples, and this is our data from which we want to learn. By comparison, the classification setting is different that we saw earlier. In the classification setting, we are just given, for example, two classes. And the two classes are supposed to indicate whether a customer is creditworthy or not. So we can have values of -1 or 1, or we can model this as yes or no. This makes no difference. We just have, for this setting, we choose the numerical representation of the classes and have the value ci for each customer. And this is then our data sets from which we want to learn creditworthiness as a classification. We can always use, and this is what I'm going to show you, the regression setting and translate that into a classification setting by making it discrete. So we can use regression, a regression function, to classify. So in order to look at how this works, we need to give a quick recap of linear regression, of what a linear regression model is. We are given a feature vector x and a linear model function. And the linear model function computes a real value by simply combining each feature value of the feature vector with a weight over all dimensions of the feature vector and adding a weight 0, another weight on top of that. This is a simple linear model function, and it gives us a real value. We can also write this model function as a vector, as a scalar product of two vectors. The feature vector is already given as a vector. It is just decomposed here into its features with the linear model function. Here we leave it as a vector and just multiply it with the transpose of a weight vector. And that weight vector simply compiles all the weights of the linear model function as well as the weight 0. The only thing in order for this function to work that we need to do is to extend the feature vector that we see here with a value for the 0 weight. And so that since there is no feature 0, we just choose 1 for that. So we have here an extended version of that feature vector where the 0th dimension is 1. If we are now given n different such feature vectors, we can assess how good a given model function with a given parameterization works as a predictor in our linear regression. For example, how well it works to predict the credit line of a customer. We can do this by simply compute the so-called residual sum of squares from given the parameter vector. And we do that by computing the model function and taking the difference to the expected value and squaring that. Or if we use the vector notation model function, we simply compute the scalar product of the parameter vector transposed, multiplied with the feature vector, take the difference to the expected value, square that and sum this over all our customers. So this is the sum of the residuals, and this then is called the residual, basically. If we want to find the best parameterization of our linear model function, the vector that minimizes this value here, the vector that best predicts the credit line worthiness, the credit line value of a customer, all we need to do is to minimize the residual sum of squares. So we need to find the parameter vector W in p+1 dimensions, which makes this error here minimal. That is all that we need to do. This is the entire optimization that we need to do. And much of what I said is written here, and a bit of extra information that will come later that I will not go into here now. If we want to visualize what is happening here, we can look at this. Let's look at the one-dimensional case. So we have just a feature vector with one feature. So if we go back to the example here, we just have, for example, income. We want to figure out whether income predicts credit line worthiness. Income is distributed over a certain number of values, and here are our n customers again. And what we can do now is we can observe that apparently with growing x, the y value here also grows. And what we can do is we can just draw a line that as much as possible fits the growth of the points here with x. And the line that we see here is actually the optimal line that can be drawn if we just want to draw a line. It is optimal because it minimizes the so-called residual sum of squares. None of the values are actually on the line here. So if this function, if this model function here, if this line is supposed to predict based on a feature vector, based on income, what is the credit line worthiness, then we are making always errors, small errors, because none of the values that the function predicts is actually the true value that we know from our data. However, if we want to use such a linear model, this is the best that we can do. This is the minimal error because it minimizes the distance of all of these points to the line, of all of these points from the line, or rather the square of that distance. And this also is true for the data that we have, and it is, if the data that we have actually continues to develop in this way, then it will also be true for any future value if we, for example, encounter a new customer here that has a higher income. If for some reason, with growing income, the credit line worthiness decreases again. So, for example, if we encounter a dot that is here, then the error will be huge. So, a different line might be in order. If we want to look closer, what happens here? So, this is the residual. So, this is the actual error that we are looking at here. We want to take the square of that, so we want to make the error as small as possible. And with the weight 0, we are deciding what is the y-intercept. So, was ist der y-Achsenabschnitt in German? Whereas weight 1 decides what is the slope, the growth of the linear model function here, in the one-dimensional case. The function is very simple. As you can see it, we can just put it into the residual sum of squares function and get this form here. How do we find this line? So how do we find the two parameters that give us exactly this line given these dots? This is something that we can directly compute using algebra. or basically analysis, functional analysis, by just taking the derivative of this function with respect to weight 0 and with respect to weight 1. This is something that you might have had already in school, or at the beginning also in the stochastics course. So by asking when the derivative becomes 0, we ask with which parameter vector, with which parameter 0, we will most likely see a 0 error in our prediction. The same for the parameter 1 here. And we can simply derive that by computing the derivative, and we will get for weight 0 this formula here. So the average of the y values minus W1 multiplied with the average of the x values of the features. So this is then the W0 value depends on W1 in this case. So if we now compute also the same for W1, we will get a value that is not dependent on any other weight, and we can just then choose to put this function in here and solve, and we will get then basically the optimal feature values for the points that we are given, the optimal parameters for the model function. We denote this then as the optimal, and this is the head notation here. So with this method, with the so-called direct method of analytically finding the minimum of the model function with respect to making errors, we find the best possible parameter vectors for the model function given this situation here. And all of this is basically what happens with what could be called stochastic gradient descent. We are in a one-dimensional case, in a situation where we can still visualize what is happening, because we are looking for parameters, two parameters, which gives us a two-dimensional situation with the third dimension of the residual sum of squares. So we are seeing here a convex function in two parameters. And for any initial choice that we are making, we can see where from given the derivative the minimum. With the direct method, we are computing directly the minimal value here. And since the residual sum of squares by construction, when it is based on a linear model function, is always convex, with the direct method we will always compute this value directly. We can go about this differently though. We can choose to use stochastic gradient descent using the LMS algorithm, and then starting from a random value, go there in small steps. We will see this later. When we want to generalize this situation to higher dimensions, to a higher dimensional feature space, we need to consider again the vector notation of the model function here. So the situation has not changed much. It is the same as we saw before. We have the residual sum of squares in vector notation here, and all that we need to do is then minimize this function again. Find the parameter values that minimize this function. Again, we can try to find that. Let me see, I'm a little bit lost right now. Yeah, okay, so we will translate this to a vector notation here, simply to make it more amenable for solving the equation that we see later. So all that we see here is that the matrix X is an n times p plus 1 matrix, which gives us all the n feature vectors, which in its rows will have the extended feature vectors, and in its columns the features themselves. And we have another vector y, which is an n vector of all the expected values for all the n customers that we have. And The square of the residual sum of squares can then be simply written like this. We have first y minus x times w transposed, again with y minus x times w. So this is basically the same as we see here, if we put that into the function. With this function, we can then again compute the minimal parameter vector by deriving, by computing the partial derivation for all weights, for the entire weight vector. So it's basically computing the derivation for all individual weights here. And this is done by setting this function to 0. So this is already the derivation, and then solving for 0. We have here the situation that we just multiply by 2, then expand the brackets, move the this part over here, and then solve for w. This is basically the situation where we want to minimize the error. This is called the so-called normal equations. So this gives us a linear equation system that can be solved, and this then is the solution by computing the inverse of this square matrix of multiplying the feature vectors with themselves. We can compute this pseudo-inverse. It's called a pseudo-inverse because our feature vectors are a rectangular matrix. It's not a square matrix. We can always compute this pseudo-inverse if and only if the features that we have chosen are linearly independent. So if we don't have a feature x1 that is then repeated another time as a feature x2, but is simply multiplied by 2, the feature x1. And that means the matrix X has full column rank. But this is only on a side note. In the end, this is just the solution for this problem when choosing the analytical method, and it gives us, just the same way, the ideal parameter vector for our model function. So what we can do is we can now set up our ideal model function for this situation. And we could simply multiply this with the customer database that we have already and find all the predicted credit line values, and thereby compute basically the goodness of fit for this function basically. We will not do this usually in practice. So we will not use the direct method in practice. We will simply, this is simply to show you that there is an analytical way to solve this problem. However, we now have the problem that computing the pseudo-inverse here is computationally expensive. We cannot solve a high-dimensional, p-dimensional problem like this with the computer in a reasonable amount of time. Usually, we are left with situations where we can reach. Let me see here. Situations where we can do it analytically in like 10 or 4 dimensions, but given modern representations of objects like texts, for example, we have way more features to represent objects than we usually encounter in analytical situations. So what we actually need is solutions like the LMS algorithm that we saw before. So what we actually need to do is we need to go back here and do this in small steps. We cannot always compute the direct minimum of the convex function of the RSS. We always have to approximate it in small steps if we go to higher dimensions. So we are seeing here now the regression situation, the way to compute the optimal parameter values for a model function using a direct method or using any other method gives us a regression function. And it learns the credit line worthiness that we wanted to learn. So this is the credit line worthiness in 1 dimensions again. But what I wanted to show you is classification. How can we do a classification based on this? Well, in the end, in the classification situation where we want to just predict credit worthiness, this is also just the output of a real value. We can just say credit worthy means 1 and not credit worthy means -1. And then all our customers are again just dots in a one-dimensional, in this case one-dimensional feature space where this is the income and this is the credit worthiness. And nothing stops us from learning a regression function to predict these values. Again, there will be residuals here. So in the end, that we need to optimize, and there is a model function, a linear model function, that minimizes these residuals, these errors here. So the only difference between regression when applied to classification is that we just look at when does this model function go from negative to positive. If we choose this as, for example, the positive class and this the negative class. So by computing the model function for any given example and looking for the sign of the scalar product here, whether it is positive or negative, we can make a decision whether the example is positive or negative. And this is basically illustrated here. We just choose this as the discrimination point, and then using the sign function on the scalar product, make a decision. It can now be that we encounter an example that exactly has the 0 value. So where the model function evaluates to 0, and then by convention we say when 0 is reached, we still call it positive. All of this can, of course, also be done in higher dimensions. Now consider the 2-dimensional case. We model our customers now with 2 features: income and the rate by which they want to pay back the credit, for example. These are the 2 features, and this is again credit worthiness. We again have a customer base, and they distribute in this 2-dimensional input space here. And at some point, there will be perhaps a situation where the customers which are not creditworthy turn into customers which are creditworthy. The farther we go on the income, and the farther we go on the payback rate, something like that. And again, we can find parameters for a linear model function that, in this case, will form a hyperplane here, in this 3-dimensional plane in this space. So what would you think now is our, how do we now decide again between the customers which are creditworthy and which are not creditworthy? What do we do? Well, we do it the same way as before. We just look when this value, the model function value, is 0. And this gives us a line in the 2-dimensional space. This line can be mapped or projected into the input space, which is just in these 2 dimensions. And if you see in a paper something like this, like a depiction of what the classification is actually supposed to do, then usually these pictures show you the input space of features, the positive and the negative example, and the line that is to be drawn. So if you see this in a book or in a paper somewhere, this is what is usually meant. Understanding this is crucial, in my view, and I want to ask you, did you understand? Could you follow? How about you? Yeah, I would have repeated it anyway. So this, since this is so crucial to understand this connection, and since there was some perhaps unexpected math in between, which is really not that complicated by comparison, but it is a little bit involved, I want to just reiterate the connection for you. So, our starting point is a linear model. We are given a number of customers, and for each customer, we know what value we want to predict. We can compute for each customer the error our model function is making. And our question is, which model function, which parameterization of the model function minimizes this error for this customer, or the squared error for all customers? And by minimizing this function, by finding that parameter vector that minimizes this function for our customer database, this gives us the optimal model function to make our prediction. And this is all that has been happening here. We can, by the way, we can choose different functions here. It doesn't have to be the residual sum of squares. We could just say we do not use the square, we just use the cube. We could use any exponent here. We could also just use the absolute difference. It's also fine. All of this is fine in that sense, that it is a function that gives you an estimation of the error that your model is making, and that error is seen here. This is the actual error, so this is what is in the brackets here, the residual, das Residuum in German, and we choose to square it. But we could cube it, we could compute any other exponent that is to our liking, no problem at all. We just need an idea of how much errors, how many errors, or an idea of the magnitude of the error that the function is making. Overall, the examples that we have. And then we need to choose the parameters which minimize that error. It happens, and this is the result that Carl Friedrich Gauss found out, it happens that choosing the exponent of the square, so the residual sum of squares, is optimal. It's the best choice one could possibly make over choosing higher dimensions or over choosing the absolute value of the error. We will see that at the end of this slide deck. But this is the best choice that one can make. It has good properties, mathematically speaking. So, interestingly, this function is convex. And due to the convexity, we can use simple analysis in lower dimensions and just compute the optimal parameter for our model function, the optimal parameters. Here, in the one-dimensional case, we have two parameters, and we can just solve the linear equations and find which is the optimal parameter by deriving, by computing the partial derivation of the residual sum of squares with respect to W0 and W1, solving for an error of 0. So we want that error to be 0. We want to find out at what parameter W0 and W1 that function becomes 0, or as close as possible to 0. And thereby we will find our optimal parameterization of the model function. This is the same as computing of that convex function, the minimum. This function is convex, I'm telling you that, but what do you actually have to do in order to find whether you have found a minimum or a maximum of a function? Yeah?
I would have to do the second derivative?
Yes, exactly. You would have to look at the second derivative. And this is basically what we have written here in the higher dimensional case as well. This is what happens here, more or less. We haven't computed it. Since we already know that this is a convex function, we don't need to do that. But usually in the general case of doing a function analysis, you would have to do that. So in the general case, here we take the residual sum of squares, we generalize it to the vector notation in order to make it amenable for higher dimensions and easier to do the math, basically, to make the derivation. We now compute the partial derivative for all possible parameters, regardless of the dimensionality. And this is simply done in an algebraic way here, in a vector or matrix algebra. So this is the derivative of the function. We want to find which parameter vector makes this 0. So we solve for this parameter vector and find that this, computing this pseudo-inverse, this matrix here, which is called the pseudo-inverse of the input matrix, our feature vector is x, multiplied by y gives us this parameter vector. And we can then use that as our model function in the end. Visually, this is our model function that we want to fit to this data. And we can do the very same thing if we have a discrete situation. So this is a continuous situation. We have some value that grows, the credit line value, and this is the classification situation where we just want to find one of two classes. We just encode our classes as 1 and minus 1 in this case. And we choose 1 and minus 1 in order to exploit the nice property of the model function that then this function has to pass through 0. And making that choice, we can then compute for every model function, for every parameterization of the model function, the error of that function in the classification setting by simply looking at the sign of that model function. So we compute the scalar product of the parameterization of the model function with the given example. We look whether it is negative or positive, and then decide whether the model function is correct or not correct. And this is only, and we optimize that classification by optimizing the regression of the model function towards this data here. Can you see flaws in this? What could go wrong? So this is the point that we want to optimize to separate the positive from the negative cases here. Or rather, this separation here. What can go wrong with this function? Can you construct in your head a situation where this function would be false? Yes.
Maybe if we had just like one person that's credit unworthy and
Yes.
a lot of like once positive cases,
Mm-hmm.
then our linear function would look kind of
Different.
Yeah.
Yeah, it would look different. So you can choose the dots here to make the function look different. How would you choose the function? How would you choose a dot here to make the function look like this?
Just add some more points that are
Yeah.
with higher x values.
Exactly. If we put a point here, then the residual to that function would become large. And the further we choose points here, the larger the residual. And since we square the residual, that distance is even higher. So that error has a lot of effect on choosing the optimal parameter value, be it in a direct method or in another method, for this model function. And it pulls the model function over here. Even if it is a positive example that belongs here on the positive side. But it then moves the 0 point of that function more to here. So in this situation, we have a well-behaved set of examples. And if all our future examples fall into these bins here, everything's fine. We don't need to care whether the model function misbehaves here or misbehaves here. But we do need to care in a situation where we have outliers, extreme outliers, which we still want to classify correctly. A linear regression cannot help here, but a logistic regression can. And we will later in the lecture see how this works, not now. So this is how we can accomplish classification using regression. And we can, of course, do so in higher dimensions, just the same way a linear model function in a higher dimensional space, in a in a three-dimensional space. Here is a plane, and here again we just look for the 0 line of the plane in order to make our decision. This is now not a discrimination point as before. This is a discrimination line. And in general, we would have a discriminating hyperplane. But this cannot be visualized anymore properly. Since if I add another feature value to the input space, I would already be in 3 dimensions. I would need to add the y dimension here, the classification output as a 4th dimension, and visualizing that does not work. Nevertheless, for this we can still see it, and if you see something like this in a paper, this is what is meant. If a linear regression or some kind of regression classifier is used. There are other ways of finding this line. For example, the support vector machine, which only works in the input space, or the perceptron, which is the basis of the neural network, which also only works in this input space. But with regression, we do something like this. We just translate the regression problem, the optimization of this, finding the optimal hyperplane to fit this data into a classification setting. All right. With linear model functions, we can do anything. What does linear mean in a linear model function? Linear does not mean that the axes are linear, like here. Let me go back. Sorry for skipping through the slides so much, but it's easier visible right in the beginning. Linear does not mean that these axes are linear. Linear means that the parameters are linear, that they do not occur in any part of the formula which has an exponent or some other nonlinearity. That is sufficient for a model function to be called a linear model function. So I go back, and we can look at things that we can do also. This is called a basis expansion, or they can do other kinds of things. We can have quantitative inputs, we can have, so this is the basic linear case, but we can also make transformations to that input. We can take a logarithm of a feature value. We can use the square root of a feature value. We can use the exponent of a feature value, as long as we don't do that to the parameter. We can encode qualitative variables simply by checking whether a given feature has a nominal value that corresponds to a certain literal. We just give each literal a number. You remember this notation from before. I'll show it to you again. What this means. We just say this could be the equivalence of the literal or something in the concept learning case. We could also combine different feature values into a new feature value, if that makes sense. This is a way of putting information into the model function. We can say that growing income does not indefinitely extend to the credit line. At some point, the credit line does not grow as much as the income. This is possible. We could say something like this. I'm not sure if it's actually said, but we could put our knowledge into this through these kinds of operations. None of this affects the linearity of the model function. The model function is linear regardless of what we do to the features. It is simply linear in the parameters of the model function. So we see x is fixed, y is the model function, and w is our set of parameters. And with this, we can do all kinds of funny things. We can learn functions like this. For example, if we have this kind of a model function and want to know which parameters separate the minuses from the pluses, so the positive from the negative, we can, again, here, linearity in the parameters, higher order polynomials in the features, we can find a parameter vector that gives us a circle as a discriminator. And this is how it looks in the model function. In fact, two features and two parameters we just ignore. We just take these squared features here and the y-intercept, and this is how we position the circle around the minuses. So we can always separate this. And in order to do a classification again, this was just the regression case, in order to do classification again, we just predict again whether this is greater or equals 1, or whether, and this is equivalent with the scalar product of the regression function being greater or equal to 0. We don't need to make any special adjustments here. We don't need to have a different kind of threshold. We just can compute for any new example whether this scalar product is greater or equal to 0. Simply by having chosen this as our discrimination hypercircle. And this is then, of course, possible to be extended to even odder shapes in the same way. So, if we want to compute what we have done now by computing the minimum directly to what we have seen before with the iterative method of the LMS algorithm, this is what we will see here. In practice, we will not be able to compute the best parameters just by analyzing the residual sum of squares function or any other function that we encounter. Still, we want our functions, our error functions or loss functions as they are called, to still be differentiable and ideally also convex like this. So they are supposed to have minima in order for us to be able to do gradient descent. With the LMS algorithm that we saw earlier, this is also possible. We can do the same with the LMS algorithm. The LMS algorithm is applicable online. It is robust. It has a robust structure. So these are just some properties of the algorithm. The convergence of the algorithm is not very satisfactory, which depends, of course, on the fact that we are just randomly choosing any examples, but not systematically looking at all examples. So we are just doing partial optimization against the data. And it allows stochastic sampling. So what happens here is basically we initialize the parameters of the LMS algorithm randomly, and it just goes step by step with the learning rate to the minimum. So this is basically a different way of looking at the LMS algorithm. We have here a signal, which is basically the object represented as a feature vector, which is in the system that we want to learn, so the system generating the data that we have as example. So we consider this to be a system now, something that generated our data for us. We use that as an example to learn the parameter vector that optimizes the model function to emulate that unknown system, basically. Yeah. And we do so by choosing one example and taking the difference to the computed value and then changing the parameters so that we get closer to what we want to actually measure. And this is what happens actually in the LMS algorithm that we saw before. With the normal equations, we just compute the optimal parameter vector, so the minimum here directly. With the LMS algorithm, we go there step by step. The problem with the normal equations is, well, we need all the data in order to make a good decision. If we only have partial data, we may end up with the wrong optimal parameter value. It's only optimal with respect to the data. Here, we have better generalization properties, probably. It is numerically unstable, so it means if the situation that you are finding with especially your feature space or the model formation function, the features that you chose, if they are linearly dependent to some extent, correlated a lot, or otherwise odd, you may find that using the normal equations or using the direct method to compute the optimal parameter vector simply fails because it is not computable, or you have many different solutions here. And that's the biggest catch. It is not applicable to big data. So if you have a huge matrix X and lots of features, it's even difficult to get this into a computer, let alone computing the pseudo-inverse, which means you have to have the square of that matrix inside the memory. There are algorithms to overcome this. There was a previous remark slide to look at. The QR decomposition goes a little bit deeper, but in general, we will use stochastic gradient descent as an optimization criterion on things like neural networks, which help us actually learn this properly. So this gets us to the question of why are we using the residual sum of squares as a loss function? Well, this is due to the Gauss-Markov theorem, who found, Gauss and then refined by Markov, found that given a data set of predictions and a linear model function, then within the class of unbiased estimators, an unbiased estimator is, for example, the residual sum of squares, but it could also be the residual sum of cubes, the residual sum of exponent 4 errors, or something like that. So within the class of all these functions, the least squares estimator has a minimum variance. That means if you choose a higher exponent, you will have a higher variance of the possible minimum. And it is therefore the most efficient one to compute. I will not prove this to you, but there are certain related and follow-up issues. What is the mean and the variance of the parameter vector? So it is definitely something that is to be considered given the data that we have. There's actually the set of the weak and the strong assumptions, which I didn't go into. You will find that on the remark slides earlier. We still have the efficiency and consistency of the unbiased estimator, as well as how to deal with the deficiencies of the input matrix X with regards to its rank. So meaning whether it is whether the columns of that matrix are linear dependent or not. And we have the relation between the different kinds of things. So this is all advanced topics that we will not go into here. Do you have questions so far? Could you follow? Okay, good. Then I will